In the grand tapestry of scientific history, certain threads shine with a particular brilliance, often against a backdrop of established dogma. One such luminous thread is the work of Kamal al-Din Al-Farisi, a Persian physicist and mathematician of the late 13th and early 14th centuries. His life and studies represent a pivotal moment in the understanding of light and vision. Born around the year 1267, Al-Farisi emerged during a period of immense intellectual vibrancy in the Islamic world. This era, often called the Islamic Golden Age, was characterized by rigorous scientific inquiry and the preservation of classical knowledge. Al-Farisi's journey into the heart of optical science began under the tutelage of the great astronomer and philosopher Qutb al-Din Al-Shirazi. Al-Shirazi, himself a student of the polymath Nasir al-Din al-Tusi, recognized the prodigious talent in his young student. He presented Al-Farisi with a profound challenge: to undertake a deep and critical revision of the paramount work on optics of the time. This was the Kitab al-Manazir, or Book of Optics, written by the 11th century master Ibn al-Haytham, known in the West as Al-Hazm. Ibn al-Haytham's work was a monumental achievement, establishing that vision occurs when light enters the eye from an object, not the other way around. For centuries, his theory stood as the definitive explanation of vision and light. Yet, Al-Shirazi had been wrestling with a particular problem that Ibn al-Haytham had not fully resolved: the true nature of the rainbow. He passed this complex puzzle to Al-Farisi, setting in motion a groundbreaking investigation. Al-Farisi embarked on this task with incredible diligence, producing his magnum opus, the Tanqi al-Manazir Lidawi al-Absar wal-Basair. This title translates to the revision of the optics for those with sight and insight. It was far more than a mere commentary. It was a creative and critical reformulation of the entire field. Within the Tanqi, Al-Farisi systematically addressed the points of difficulty in Ibn al-Haytham's theories. He did not seek to diminish the master, but to build upon his foundation, correcting and refining his conclusions. The most spectacular part of this revision was his entirely new and mathematically robust explanation of the rainbow. Ibn al-Haytham had proposed that the rainbow is formed by light reflecting from a concave cloud surface. Al-Farisi, through logic and experiment, demonstrated that this model was incorrect. He argued that the phenomenon occurred within the individual water droplets themselves. To prove his hypothesis, Al-Farisi designed an ingenious and elegant experiment. Took a large, transparent sphere of glass and filled it with water. This water-filled sphere was to serve as a magnified model of a single raindrop. He then placed the sphere in a dark chamber, a camera obscura, to control the light. A single beam of light was allowed to enter the chamber and strike the glass sphere. By carefully observing the path of the light, Al-Farisi could trace its journey. He documented that the ray of sunlight first refracted as it entered the water-filled sphere. This initial refraction caused the white light to begin to disperse into its constituent colors. Then the light traveled to the back inner surface of the sphere. Here, it underwent a total internal reflection, bouncing off the back of the droplet. Finally, the reflected light traveled back to the front of the sphere and refracted again as it exited. This second refraction further separated the colors, creating the visible spectrum. Al-Farisi had successfully modeled and explained the formation of the primary rainbow. His explanation was a masterpiece of the scientific method, combining theory with empirical verification. He did not stop there. His inquisitive mind pushed the boundaries even further. Al-Farisi also investigated the secondary rainbow, the fainter arc sometimes seen above the primary one. He correctly deduced that this was formed by light undergoing two internal reflections within the water droplet, not just one. This explained why the secondary rainbow is always fainter, and why its colors are reversed. Each reflection and refraction caused the light to lose some of its intensity. This model of the rainbow was so accurate that it would not be significantly improved upon for over 300 years. Theodoric of Freiberg, a contemporary in Europe, independently reached similar conclusions around the same time. This parallel discovery highlights the universal nature of scientific inquiry. However, Al-Farisi's work was arguably more mathematically rigorous and comprehensive. Beyond the rainbow, Al-Farisi also made crucial contributions to understanding the camera obscura. Ibn al-Haytham had used the camera obscura to demonstrate that light travels in straight lines. Al-Farisi's experiments with the aperture of the camera obscura revealed more subtle phenomena. He investigated why the image of the sun, when projected through a small, non-circular aperture, still appeared circular. He correctly theorized that the light rays from the sun's disk, being an extended source, effectively paint a circular image. This was a sophisticated insight into the nature of light sources, and Al-Farisi also delved into the nature of color itself, a topic of much philosophical debate. He rejected the Aristotelian idea that colors were simply a mixture of light and darkness. Instead, he proposed that colors were phenomena of light itself, a truly radical idea for his time. He argued that darkness was merely the absence of light, not a substance to be mixed with it. His experiments showed that different colors were produced by the modification of light through refraction and reflection. This was a crucial step away from metaphysics and towards a physical theory of color. Al-Farisi's intellectual curiosity was not confined to optics alone. He was also a gifted mathematician who made significant contributions to number theory. He wrote a treatise called Tadkirat al-Abab fi Bayan al-Tahab, Memorandum for Friends on the Proof of Amicability. In this work, he explored amicable numbers, pairs of numbers where each is the sum of the proper divisors of the other. He applied new mathematical ideas, including a major new theorem on factorization. This work demonstrated a deep understanding of number theory that was far ahead of his European contemporaries. Kamal al-Din al-Farisi's death, around 1319, marked the end of a profoundly productive scientific life. His legacy, however, was cemented in the pages of his brilliant Tanqi. He exemplified the spirit of scientific progress, respecting the past while courageously questioning it. His work on the rainbow was a triumph of experimental physics and mathematical modeling. He provided the first truly satisfactory and scientific explanation for one of nature's most beautiful spectacles. His refractions of light were also refractions of thought, bending the course of science towards a brighter, more accurate future. The foundations of optics were shaken and rebuilt by his careful, methodical hands. His mentor, Al-Shirazi, had seen the problem, but it was Al-Farisi who provided the solution. The use of a large-scale model was a revolutionary step in experimental design. It allowed for the direct observation of phenomena that were impossible to see in tiny raindrops. This method bridged the gap between abstract mathematical theory and tangible physical reality. He meticulously recorded the angles of incidence and refraction, gathering quantitative data. This quantitative approach was a hallmark of the new physics he was pioneering. He demonstrated that the primary rainbow is seen at an angle of approximately 42 degrees from the observer's shadow. And he calculated the secondary rainbow's position at around 51 degrees. These values, derived from his model, corresponded perfectly with real-world observation. The Tanqi was not just a book on optics. It was a lesson in how to do science. It showed the importance of questioning authority, even one as revered as Ibn al-Haytham. His critique was always respectful, framed as a revision or correction, not a demolition. This intellectual humility, combined with fierce curiosity, was the key to his success. His work on the camera obscura also clarified the relationship between the aperture and the image. He understood that a point source of light would create a sharp image of the aperture itself. But an extended source, like the sun, acts as an infinite collection of point sources. Each point source projects an image of the aperture, and these overlapping images create the final projection. This explanation resolved a long-standing paradox in the theory of the pinhole camera. Al-Farisi's insights into color were equally profound, separating it from philosophical concepts of darkness. He established color as an intrinsic property related to the physics of light. This laid the groundwork for Newton's later, more detailed work on the spectrum. The intellectual environment of Tabriz, a crossroads of cultures, surely fueled his work. Here, ideas from the East and West could meet and be synthesized. The Maraghe Observatory, established by Al-Tusi, had created a legacy of scientific rigor in the region. Al-Farisi was a direct intellectual descendant of this tradition. His contributions were not isolated flashes of genius, but the culmination of a thriving scientific culture. Demonstrated that scientific knowledge is a cumulative process of refinement and correction. Each generation stands on the shoulders of the giants who came before. Al-Farisi's revision of the Book of Optics is a perfect embodiment of this principle. He honored Ibn al-Haytham by engaging with his work at the deepest possible level. The quest for understanding the rainbow was a quest for understanding the divine order of the cosmos. For medieval scholars, science and faith were not in conflict but were two paths to the same truth. To understand the laws of nature was to appreciate the wisdom of its creator. Al-Farisi's work, therefore, had both scientific and spiritual dimensions. His explanation demystified the rainbow without diminishing its beauty. It showed that the beauty of the natural world could be appreciated even more through understanding its mechanisms. The light that passed through his glass sphere illuminated the minds of scientists for centuries to come. His name deserves to be remembered alongside the great figures of the scientific revolution. He was a physicist who used refraction to understand refraction itself. His work was a brilliant reflection on the nature of light, color, and perception. The world of physics is richer for the questions he dared to ask. And it is more complete because of the answers he painstakingly found. The study of light is the study of the universe's primary messenger. Al-Farisi dedicated his life to deciphering the language of this messenger. Showed that even the most ephemeral beauty is governed by precise, understandable laws. The rainbow's arc is a perfect curve drawn by the laws of physics. Al-Farisi was one of the first to reveal the compass and the ruler behind the painting. His experimental setup was a microcosm of the sun, atmosphere, and observer. He controlled the variables to isolate the cause, a key tenet of modern science. The darkness of the camera obscura was essential for making the faint colors visible. This mirrors how the darkness of space allows us to see the faint light of distant stars. Al-Farisi's mind was a camera obscura of its own, filtering knowledge to project a clearer image of reality. Took the diffuse light of a complex problem and focused it into a sharp, elegant solution. The legacy of the Islamic Golden Age is embodied in scholars like him. They were not just preservers of ancient knowledge, but active creators of new understanding. The scientific method was not born in a single moment, but evolved through the work of many. Kamal al-Din al-Farisi represents a powerful current in that mighty river. His explanation of the rainbow stands as a monument to human curiosity. It is a story of how a persistent question can lead to a revolution in thought. He proved that the world is not only beautiful, but also intelligible. And in that intelligibility, there is a deeper beauty to be found. The physicists' refractions revealed the hidden mathematics of the heavens. His work reminds us that every natural wonder contains a scientific secret waiting to be told. Al-Farisi listened carefully to the story told by the light, and in his revision, he translated it for all the world to hear.